When we start the induction motor, it is going to draw a very large amount of current. Why is that? Because at starting, the slip S is equal to 1. So the resistance R2 dash by S is going to be much smaller than it is under normal operating conditions. To be much smaller than at normal operating condition. Because at normal operating condition, the value of S is going to be much smaller. So that R2 dash by S will become a very large value. So once the resistance is small, then the current drawn will be high. Okay. This is the reason we are discussing this topic. We need to use some starting methods so that we reduce the amount of current that can be drawn at starting. Now whatever methods we use, we also need to ensure that the starting torque is not reduced too much. What is the starting torque? This can be written as 3 by omega square into I2 dash whole square into R2 dash, because S is equal to 1. Since S is equal to 1. What will be the full load torque? If you take TFL as the full load torque, then this is going to be 3 by omega S into I2 dash whole square into R2 dash by SF. Okay, where slip SF is the slip at full load. If you ignore the magnetizing current, that means if you remember the equivalent circuit, this is the magnetizing component I naught and this is I2 dash. Right, here we are going to have R2 dash by S and JX2 dash. Now this is the current that is actually drawn from the supply. Now this current can be ignored in comparison to the current I2 dash. At starting anyways it is very high, so you can ignore the no load current which is very small compared to the high starting current. Even at full load, this no magnetizing current, it can be neglected in comparison to the I2 dash. Neglecting magnetizing current, which is negligible compared to high starting current as well as full load current. So neglecting the magnetizing current, I2 dash will be the current drawn from supply. Okay. So what we can write, the starting torque Ts is equal to 3 by omega S into the starting current if you take as Is whole square into R2 dash, where Is is starting current and the full load torque TFL is equal to 3 by omega S into the full load current whole square into R2 dash by SF. So what will be the ratio of the starting torque and the full load torque? So it's going to be the starting current divided by the full load current whole square into the slip at full load. Okay. This will give us an idea about what will happen to the starting torque when we use various starting methods. First starting method is direct online. That means there is no specific starting method. Directly whatever voltage that is given at operating condition, normal operating condition, we give the same voltage. So the starting torque with respect to the full load torque, as a ratio of full load torque, it will simply be equal to the starting current divided by the full load current into the slip at full load. Now here what will be the starting current? It will be nothing but the short circuit current. That means the current drawn at blocked rotor test. whatever the current you get at under a blocked rotor test, that is the short circuit current. So the starting current will be nothing but ISC. Now if the starting current is 5 times the full load current also, then what will happen? For example, this is just to get an idea about what will be the magnitude of starting torque for this much amount of starting current. If starting current is 5 times the full load current and the slip at full load, it will usually be 2% to 8%. So then the starting torque by the full load torque will give you 5 times whole square into, let us take 0.04% of full load slip, and this is going to be 1. So that means even though the starting current, the torque is proportional to the square of current, even though this current is 5 times the full load current, the starting current is still only equal to the full load current. This is for the direct online starting. If it is other methods of starting, it will be further less. Okay. So what we use is usually reduced voltage is what we use for starting. In this, there are various ways in which we can reduce voltage. The very first method is the stator impedance starting. Here what happens? Resistance or inductors also are included in the stator feeding circuit. Basically, if this is the 3 motor lines, then you are going to have resistances here before the supply is given. As the motor approaches normal operating condition, these can be slowly shorted away. So in this case, let us say the voltage is reducing by a fraction x. Okay. So xv will be the new voltage at starting, where x is fraction by which voltage is reduced. And what will happen? The starting current also will be reduced by x times. So that means x of short circuit current, because under direct line starting, Is will simply be equal to Isc. Here it will be equal to x times Isc. Now what will happen to the torque? Ts by Tfl will be equal to x times Isc divided by full load into Sf. So this is going to give you the starting torque x square times Isc whole square by Ifl whole square into Sf into finally the full load torque. So now this value, this is nothing but the torque under direct online starting. So that means the starting torque under stator impedance starting will be reduced by x square times that of the torque that you get at direct online starting. That is why whenever you use all of these methods, the motor should only be started at no load or a very light load. So you can write starting current reduces by x times and the starting torque reduces by x square times. Okay. The next method that we have is the auto transformer starting. So here what is going to happen? So this is the stator winding, the 3 phases of the stator winding. Usually it is connected in star, it can be delta as well. Now auto transformer we take like this. Now the supply is given to this auto transformer. Okay. So the starting current from the supply is some starting current IST, let us say. Now if this phase voltage is V1. Then to the motor we are going to give a reduced voltage, so that the voltage that is appearing across the stator winding per phase of the stator winding is some X times V1, so that the current that is flowing here is X times ISC. That means the X times the value of short circuit current. Similarly for all the three phases. Okay, so this is the second phase. Similarly, you're going to have for the third phase. Now this auto transformer, it can be disconnected at normal operating condition using a switch circuit. So this connection is only at starting. Connections only at starting. So you can see that the motor current will be reduced by X percentage. Then what will happen to the torque? The torque will once again be reduced by X square times only. You can do the same calculations as in the previous case, stator impedance case. Now, but one thing that you can see here is the current that is drawn from the actual supply is different from the current that the motor is taking. Now, we know that the input volt ampere of the transformer is equal to the output volt ampere. So, what will be the input volt ampere? The current flowing is IST and the voltage is V1. Okay. So, IST into V1 will be equal to what is the output volt ampere? This is X times ISC, X times V1. So, you are going to get X ISC into X V1. So, this means that the starting current IST is equal to X square times ISC. So, that means the current that is drawn from the supply is reducing by further another X fraction, X square times the short circuit current. Okay. So, this is the advantage of auto transformer. Starting current taken by motor reduces by X. Now, the starting current taken from supply. So, both are different. The current taken by motor is different from the current taken by the supply. This reduces by X square times. And finally, the starting torque again reduces by X square. And finally, the last method that we have is the star delta starter. So, here what happens, this is going to be used only for a delta connected machine, induction machine. So, what is going to happen here? If you consider the three phases of the stator winding like this. Now, each of these ends, they are taken like this. Here by means of a TPDT switch. What is the full form of TPDT? Triple pole double throw. Okay, that means there are going to be 3 poles and it can have 2 positions. So, this is one position of the switch. You are going to have a short circuit if you are going to connect in this position. So, what kind of connection will it give you? It will give you a star connected stator winding. Now, if we want delta connected stator winding. So, if you take this to be the phase A, B and C. How can we get a delta connected winding here? This is one line. Now, from B we get like this, and from C you are going to get like this. So, now if the switch is in this position, then it is going to be in the delta connected configuration. So, you can check it out for yourself. Say this is A1, A2, B1, B2, C1 and C2. Now, if the switch is in this position, what is going to happen? This point here is A1. A1 is going to be connected with C2. So, the stator winding A1, A2 will now be connected with this point is C2. So, here C1 will come. Now, where will C1 be connected? This middle line is C1. It will be connected with this middle line. So, this is going to B2. So, you are going to have the third winding here this is B2. So this should be B1. Now B1 and A2 should be connected here. So where is B1? This is how B1 is coming. It's connected to this line which is connected to A2. Okay. So this is how using a TP-DT switch we can switch from a star connected winding to a delta connected stator winding. Now these three lines, they will be given to the power supply. So let us see what will happen to the starting current, by how much it will reduce. At starting, it is in the Y configuration. So what will be the phase voltage? It will be equal to the line voltage divided by root 3. This means that the starting current IS is going to be equal to, we can take voltage VL by root 3 divided by the impedance offered under short circuit condition, right? This is the starting current when you are using the star delta starter. So this is going to be 1 by root 3 times the short circuit current. This is using the star delta starter. If you are using direct online, then what will be the condition? Without starter, now the entire line voltage will appear across each of the phase. So V phase will be equal to VL. Now what will be the phase current? The starting phase current I phase will be equal to VL divided by ZSC. So that means this will be equal to the short circuit current. But this is the current through each of the phase. What will be the line current? In a delta connected winding, the line current will be root 3 times the phase current. So this will become root 3 times ISC. So this is without star delta starter. So you can see starting current using the starter will be 1 by root 3 times short circuit current, whereas this becomes root 3 times ISC. So what will be the reduction in starting current? This will be equal to starting current with starter divided by the starting current without starter. So what will this be? With starter it was ISC by root 3 and this is root 3 ISC. This is the power current that is drawn from the supply. So this is going to be 1 by 3 times. So there will be a 1 by 3 times reduction in the starting current when we are using a star delta starter. This is just like auto transformer starter only, except that the reduction, that is the X value, is equal to 1 by 3. Okay. Now what will be the reduction in the starting torque? You can calculate in a similar manner. TS by TFL will be equal to ISC by root 3 divided by I full load whole square into SF. What about without the starter? It is going to be TS by T full load is equal to, we are concerned about the phase current here, not the current which is drawn from the supply. Okay. So it will be ISC by IFL whole square into SF. In order to differentiate, you can write TS1 and TS2. So what will be the reduction in the starting torque? Reduction in starting torque because of the starter. This is going to be starting torque with starter divided by the starting torque without starter. Okay, so what is this going to be? TS1 divided by TS2. So you're going to get ISC by root 3 divided by IF whole square into SF into the full load torque divided by ISC by IF whole square into SF into the full load torque. So what are you going to get? You're going to get simply 1 by 3. So the reduction in starting current drawn from the supply is 1 by 3 times, and the starting torque reduction is also 1 by 3 times. So you can write, therefore, reduction in starting current will be 1 by 3 times, and the reduction in starting torque is also going to be 1 by 3 times. So all of the methods that we have seen, they are predominantly used for squirrel cage motors, but they can also be used for slip ring motors. But in addition to all these methods, the slip ring motor is going to have additional method of starting. What is that? By introducing external resistance, external rotor resistance, simply because it is possible to add rotor resistance in a slip ring motor. In the squirrel cage, it is not possible because the rotor conductors, they are in the form of conductor bars. Okay. So we have already seen in the torque slip characteristics, the starting torque, it can be, let us say this is a typical characteristic of the induction motor. This is the speed axis. Now this is at a particular resistance. If you increase the rotor resistance, what is going to happen? It is going to shift. The maximum torque will remain the same, but it will start occurring at a smaller slip, and the starting torque is going to become higher as you increase the resistance. So what will happen? Let us say this is the resistance that you are keeping. R2 dash is the resistance you are keeping at starting. Now as it goes into normal operation, the resistance, the external resistance can be slowly cut away. Okay. So that under starting we have high resistance, and while operating under normal operation you are going to have lesser resistance. So how will it affect the starting current? Starting current will, the current will reduce with an increase in resistance, that is anyways there. So this is how the external rotor resistance is going to help increase the starting torque as well as reduce the starting current. So you can write increase in external rotor resistance during starting will increase starting current, starting torque. And what will happen to the starting current? It will decrease, and decreases the starting current as the motor goes into full speed. The external rotor resistance can be removed in steps. Okay. So these are all the starting methods that are available for induction motor.